2 billion years ago, Earth was a very different planet. The continents, the oceans, the very atmosphere you would breathe, or rather choke on, were almost unrecognizable compared to today. If a human could step into that world, survival would be impossible. The air itself, the light of the sun, and even the colors of the oceans bore little resemblance to the Earth we know. This period sits at a crucial moment in the history of our planet. It was the time of one of the greatest transitions in Earth's evolution, a shift from a planet dominated by simple microbes to one beginning to lay the groundwork for complex life. But that transition was violent, slow, and world-changing. To understand Earth 2 billion years ago is to witness a planet in the middle of redefining itself. The first and most immediate difference would be the air. At this time, the atmosphere was undergoing what scientists call the Great Oxidation Event. For nearly 2 billion years before this, Earth's skies were almost entirely devoid of oxygen. The world was dominated by carbon dioxide, methane, nitrogen, and other gases, giving the sky likely a hazy, orange, or even greenish tint depending on local chemistry. But around 2.4 billion years ago, cyanobacteria, tiny, photosynthetic microbes, began releasing oxygen as a byproduct of photosynthesis. At first, that oxygen did not build up in the air. Instead, it reacted with iron dissolved in the oceans, forming vast layers of rusted iron that sank to the seafloor. These deposits, called banded iron formations, are still mined today. By 2 billion years ago, this process had begun to transform the entire planet. The seas had been scoured of most of their free iron, and oxygen was finally starting to accumulate in the atmosphere. But the levels were still nowhere near what they are today. Oxygen concentrations were only around 1 to 10% of modern levels. For humans, this would be a suffocating environment, impossible to survive without technology. For microbes, however, this change was revolutionary. Oxygen was not just a new waste product, it was also a potential source of far greater energy than earlier metabolic pathways. Life was about to discover how to burn fuel more efficiently. Looking across Earth's oceans 2 billion years ago, you would not see the deep blue expanses we take for granted. Instead, vast stretches of water were green, purple, or even blood red. These strange colors came from the dominance of microbial life. In the shallow seas, mats of cyanobacteria grew in thick, slimy colonies called stromatolites. These structures still exist in places like Shark Bay in Australia, but back then, they were far more widespread, carpeting coastlines in layered, rock-like growths. Below the oxygenated surface waters, the deeper oceans remained largely anoxic, devoid of oxygen. These waters were often rich in hydrogen sulfide, a toxic chemical produced by sulfur-loving bacteria. The boundary between oxygen-rich and oxygen-poor waters was a deadly frontier. Floating microbes colored the seas in vivid hues depending on their chemistry. Purple bacteria that used sulfur instead of oxygen for photosynthesis, or green sulfur bacteria thriving in dimly lit depths. For much of Earth's oceans, this euxinic state, anoxic and sulfide-rich, made them hostile to most complex life. Yet for microbial communities, it was an ideal world. They dominated every niche, from sunlit surfaces to dark, chemical-rich vents on the seafloor. 2 billion years ago, the continents themselves were also taking on a new form. Earth's surface was not yet arranged into the continents we recognize. Instead, it was dominated by an ancient landmass known as Columbia or Nuna, one of the first true supercontinents. Geological evidence suggests that Columbia stretched across much of the equator, linking what would later become North America, South America, Africa, and parts of Asia. Unlike the rich, forested continents of today, Columbia's surface was barren. There were no plants, no soils full of organic life. The land was mostly rock, sand, and dust, with only microbial films clinging to some surfaces. Weathering was different, with bare stone interacting directly with rainfall and atmospheric gases. The assembly of Columbia also meant mountain building. Where continental plates collided, ranges of peaks would have risen, eroded, and reformed in cycles long before the familiar mountain systems of today. These mountains fed minerals into the oceans, fueling microbial growth and further altering global chemistry. 2 billion years ago, the sun itself was also different. It was younger and dimmer, about 10% less luminous than it is now. This creates a paradox. With a weaker sun, Earth should have been frozen solid. Yet evidence shows liquid water was abundant. This contradiction, known as the faint young sun paradox, remains one of the great puzzles of planetary science. The solution lies in greenhouse gases. Although oxygen was beginning to rise, carbon dioxide and methane were still present in higher concentrations than today. These gases trapped heat, compensating for the dimmer sun and keeping the planet warm enough for liquid oceans. However, climate was not stable. Geological records suggest cycles of glaciation, so-called snowball Earth events, were possible, though the most extreme versions would come later. Earth 2 billion years ago may have swung between warm, greenhouse conditions and icy periods where glaciers stretched toward the equator. But the most profound transformation of this era was not geological or atmospheric, it was biological. For nearly 2 billion years, life had been restricted to simple, single-celled organisms, bacteria and archaea. These were masters of chemistry, able to extract energy from almost any environment. But complexity was limited. Around 2 billion years ago, something extraordinary began to happen. Life discovered cooperation at the cellular level. Fossil and genetic evidence suggests this was the time when the first eukaryotes appeared, cells with internal structures, including a nucleus. This step would eventually lead to multicellular organisms, plants, animals, fungi, but for now, it was only a tentative beginning. Eukaryotes arose, it is thought, through symbiosis. A larger cell engulfed a smaller bacterium capable of using oxygen to generate large amounts of energy. Instead of digesting it, the larger cell and the smaller bacterium formed a partnership. Over time, that bacterium became the mitochondrion, the powerhouse of eukaryotic cells. This was a turning point in the history of life, opening the door to complexity. At the same time, life was leaving its mark on the planet itself. Microbes were altering the chemistry of the oceans and atmosphere on a global scale. The rise of oxygen was not just a biological byproduct, it was an evolutionary force. Many anaerobic organisms, poisoned by oxygen, retreated to deep, anoxic environments. Others adapted, using oxygen to thrive in new ways. By 2 billion years ago, Earth was a planet in transition. Oxygen was rising but not yet abundant. Continents had assembled into one of the first supercontinents, but their surfaces were barren and lifeless. Oceans were alive with microbes but toxic to complex organisms. The sun shone dimmer, yet greenhouse gases kept the world warm. It was a strange and alien planet, familiar in its seas and skies, yet utterly inhospitable to us. A world balanced between its ancient microbial past and the distant possibility of complex life.